So we are starting with Chapter 8. I will also tell you I'm not a big person that follows the textbook. Like I'm not going to do example, say, hey, all right, everybody turn to page 334 and, follow along in the book, and then we're all going to do example 1 together. That's not typically how I teach. I usually make up my own examples. I will use some of them from time to time because sometimes just finding a good example is important to be able to understand how things work. Most of the time you can make your own up once you get the hang of it like I do. So if you even look at page 334, it has our exponent properties that we're going to start with. And that is the first thing that we're going to talk about. And I don't expect these to be new. I expect these to be mostly review. Okay? Your exponential properties. And I don't even write them the same way the book does, because the book uses weird letters. Like it uses M's and N's. Who uses an M and an N when you're talking about, like, why M and N? You could pick, there's so many better letters than those. They sound alike, they kind of look alike. Like, you might as well throw an I and an O in there. Might as well, right? So I ain't using M's and N's. It's just dumb. Okay, so most of this you should already know. Should just be review for most of today. Your exponent properties. If you have any number and you are multiplying it by another number with the same base, and you are raised both of those to exponents. So for example, is if you have 5 to the third times 5 to the fourth, what do you do with your exponents? You do not times the exponents then. You add them together. I was thinking of A plus B. So the answer to this would be 5 to the 7th. You're thinking of powers raised to powers. We'll get to that one. Yeah. So we'll get to that one. But yes, you add those. The reason this works is very simple. What does 5 to the third mean? It means 5 times 5 times 5. And so times, and then what does 5 to the fourth mean? 5 times 5 times 5 times 5. Well, isn't that just all times? And don't you really just have 7 5s there and 5 to the 7th? So that's why that property works. So subtract. So that's x to the a minus b. Make sense? Okay. Now, once you have rule number 2, where you're subtracting, we have to have a couple rules that take care of potential issues. What kind of an issue could you run into? Something weird where once you subtracted your exponents, you have a problem. You can have negatives. So we have to have a way to deal with negative exponents, because you could have a problem, for example, 5 to the third divided by 5 to the 8th. So you subtract and you get 5 to the negative 5. Well, now what do? I got a negative exponent. What does that mean? Well, what do we do with negative exponents?
You have to put it over one side and move it, so that way you can make the exponent positive.
Yes, the rule is you're going to basically take the reciprocal. And I'm careful of the way I word that because yes, while I'm writing 1 over that, technically you're really just taking the reciprocal, because if the negative exponent is in the numerator, yeah, you put it in the denominator. But what happens if you have a negative exponent in the denominator? You put it in the numerator, right? So don't just think of it as 1 over. Think of it as you got to move it. If it's in the top, you got to put it in the bottom. If it's in the bottom, you got to put it in the top. And then you make it positive. Here's the one thing I need you to understand. If you see a negative exponent, is that a negative number? Is this whole thing a negative number? No. That is a positive number. Typically speaking, negative exponents just mean small numbers. That just means you have 1 over 5 to the 5th. And 5 to the 5th is a very big number. Well, 30,000 something. And it's 1/30,000th roughly. So that just means a very small number. But it also could mean a very big number. How would it be a very big number? If you have an example of like, what is 1 over 3 to the negative 8th power? Is that a very small number or a very big number?
Very big number.
That's a very big number.
It's flipped over.
Right, because it got flips and it goes back to the top. So now that's 3 to the positive 8th power in the numerator, which is now a very big number. So typically speaking, we think of negative exponents as meaning they're going to end up being very small numbers, because that's most of the time you run into them. But if it is in the denominator, it's the opposite. Make sense? All right, so what other weird thing could happen when you once you subtract your exponents? You could end up with 0. You subtract 5 to the 3rd over 5 to the 3rd. Well, 3 minus 3 is 0, so you get 5 to the 0. What do you do when you have zeros in your exponent? It always equals 1. Unless, oops, did that wrong. Unless x equals, or x basically cannot equal 0 in this case. Does everybody understand what these, when you put a colon and then you put a little bit more to the rule? Do you guys know what that means, or how we deal with that? So all that is a mathematician covering his butt. It's really what it is. Mathematicians are jerks. They really are. So if a mathematician, let's say I come up with a new theorem, right? The Fink-Beiner theorem of algebra. I found a new way to solve quadratics or something. So I plan it all out. It works right. It works perfect. I write a paper. I publish that paper, and I put it in math journals. And what do you think every other mathematician in the world immediately starts doing? Nope, they don't want to use it.
Try and find a different way to.
No. They find something wrong with it. They try to prove me wrong. They try to say, you know what, that is not right. Because if it was right, I'm smarter than you. I would have figured it out first, because that don't work. They do that. Like that's the world of mathematicians, is one person says something, and all of a sudden thousands of other mathematicians around the world are going, nuh-uh, that can't work. There's no way. And they try to find even one instance where your theory is false. If I don't put this little asterisk here, basically, of this is the theorem, this works all the time. Well, except that one little case. We got to put that on there. Because if I don't put that on there, someone's going to go, hey, dude, that can't work. Because what about 0 raised to the 0 power? That's not 1. That doesn't exist. So, ha, ha, ha. Nobody should ever listen to you ever again. Why? You were wrong. No, this is the theorem. This is just the, I want to cover my butt so nobody yells at me kind of thing. Okay? Doesn't work in that case. All right. Rule number 5. We'll go with your rule. What do you do when you have a number raised to an exponent and then that is raised to another exponent? Now you times them. So that's x to the a times b. I'm not doing examples for all these. Do you want them? Do you want an example for that one? Okay, pretty easy. And that rule also holds true. Well, so on. How about when you have x times y, you have two numbers, they are both raised to a power. What do you do in that case? Huh? They both get it. So x gets raised to the a, and the y also gets raised to the to the a power. A lot of people think of it as distributing. It's not technically distributing, but it kind of is. Now, does that rule work if it's addition and subtraction on the inside? Here's what I mean. If you have x plus 2, and that's raised to a power, does that equal x squared plus 2 squared? That's a rule, that's a mistake that people make, that I say, if you do that, you just killed a puppy. It's like a puppy just died because you did that. Of course you can't do that. What do you have to do if you have a quantity squared and it's addition or subtraction? Don't you have to do x plus 2, and then that's times x plus 2, and then you got to FOIL that out, right? The answer actually should be x squared plus 4x plus 4, right? Yes? So that rule where everything gets the power, this one, only works if it's what? Multiplication, or rule number 7, it also works if it's division. So you get x to the a over y to the a. Make sense? Okay. Rule number 8, we kind of switch gears a little bit. What do you do if you deal with a fractional exponent? X raised to the a over b. What's another way to write fractional exponents? Huh? No, you could, but that doesn't really get you anywhere. I'll give you a hint. They're fun. They're a little crazy. Starts with the letter R. What? Radical. Because radicals are crazy, right? Because that's what radical means. So you can rewrite them as radicals. Now, one of them stays as an exponent. The other becomes the root of the radical. Which one? Numerator, denominator. Where's the root? Denominator. That's your root. The numerator stays as an exponent. And you can write it like that, or you can write it as the b root of x, and then that whole thing is raised to the a. Both of these are correct, depending on the situation, the problem. Sometimes it's easier to take the root first, make it smaller, then deal with the exponent. Sometimes it's easier to deal with the exponent first and then the root. If you need a mirror, I have one in my back closet. Yeah. Yeah. Or just go in that office and open the cupboard. There's a mirror in there. So, all right. Are we good with these? All right. Go ahead. There's one more basic skill from last year, basically, that I need you being able to do. And that is to take something like, I don't want to switch pages because I know you're still writing. Take something like the square root of 72 and simplify that. How do you simplify the square root of 72? Anybody remember? You got to break it down, right? So you got to find any two numbers that multiply together to get 72. Now there's lots of different numbers that can multiply to 72. You give me one. 8 and 9? Yes? 8 times 9? 72? Make the trees? Now, a lot of people will say, look for your perfect squares. Like 4, 9, 16, 25, 36. Because we could have done 2 and 36 here, right? And then, but no matter what, you break those down. It really doesn't matter how you break it down. You just, so the 8 became the 2 and the 4, and then the 9 became the 3 and the 3. Once you get it to this point, I like to think of it as you only worry about the lead. Do we care about this 9 anymore? Why not? 2 3s. So I don't care about this branch because it went down farther. I only care about the endpoints. I don't care about this 8. I'm not even going to look at that 4 anymore, because that 4 became 2 2s. I'm only going to look at the 3, 2, 2, and that 2. And what am I looking for? I'm looking for pairs. What do I have a pair of? I got a pair of 3s, so that means I can pull a 3 out. 2 on the inside is 1 on the outside. What else do I have a pair of? I got a pair of 2s, so I can also pull a 2 out, right? Do I have any leftovers? I got that leftover 2 right there, don't I? So that leftover stays on the inside. And then all I do is multiply the those together, 6 root 2. Make sense? Easy? Vaguely remember how to do that? Should have done it a whole bunch last year. So, I'm kind of done teaching this section. But I want to do some examples that you're going to get for homework. So, I'm going to put you in the shoes of this author for a second. Okay? You're the author of this textbook. You just got done explaining all these exponent properties, right? We should probably do some practice on those exponent properties, yes? When do you add? When do you multiply? When do you subtract? All that stuff. What do you think problem number 1 should be? You're going to make up a problem, make somebody do a problem. What kind of problem do you think we should put on there? Give me some numbers. Give me an actual problem that the book should have as a problem. Just don't look in the book. Just make one up. 6 to the 4th times 6 to the 8th. That would be a reasonable question, because the answer is 6 to the 12th. Done. Let's move it on, right? Maybe they do a third problem could be a 3 to the 4th raised to the 3rd power. The answer would be 3 to the 12th. I don't know why I did that. I'm just seeing if you guys are paying attention. 3 to the 12th power. Yes? That would make a whole lot of sense. Here's what the actual book does, though. They're going to say, what is 3 to the 30th? All right, jerks, losing big numbers. Raise that to the 120th. Oh, those jerks, they put big numbers. Oh, but then they're even meaner because they put those under square roots. Now, what's our rule tell us that we have to do? What do we do with our exponents? What am I going to do with that square root of 30 and that square root of 120? I'm going to times them. Now, I prefer to simplify before I times, because if I times right now, I'm going to be dealing with big giant numbers, and then I got to simplify big giant numbers. I don't know about you, but the bigger the numbers are, the harder the problem typically gets. So what I'm going to do is I'm going to simplify. I'm going to start with that one right there. I'm going to simplify that too. Off to the side, I'm just going to break that down. What's that break down into?
60 and 2.
You could go 60 and 2. I'm a big fan of it. Ends in a 0. 2. Let's go 10. Like this, 10 and 12. Isn't that easy? If it ends in a 0, start with a 10. 10 breaks down into 5 and 2. 6 breaks down into 6 and 2, and then 2 and a 3. And again, I am never going to look at that again. I'm never going to look at that again. I'm never going to look at that again. I'm only looking at the endpoints. What do I have a pair of? I got a pair of 2s. So I can pull a 2 out. Any more pairs? Shucks. Everything's got to go back on the inside. If I put all that back on the inside, that 2, that 3, and that 5, what do I have on the inside? 30. What that means is this problem is the same as 3 to the square root of 30 raised to the 2 root 30. And I know I can't break down that square root of 30 because that's just going to break down into 2 and 3 and 5 again, and I'm not going to have any pairs. Now I multiply, because that's my property. What's square root of 30 times square root of 30? It's 30. Like the square roots just cancel, and it's square root of 30. So 30 times 2, what is my answer? 3 to the 60th power. You're done. Do you guys see where I got 60 from? Now, the next question becomes, do you want me to calculate that, or should I leave that as an answer? Here's where I personally want you to use some common sense. Anybody know about how big 3 to the 60th power is? It's about that big. It's probably got less than 35. It's 28 numbers long. Do you think I want a number that's 28 numbers long on my paper, on your homework? No, that's pretty. Leave it alone. If the answer comes out to 2 to the 3rd power, do you think I want 2 to the 3rd power, or do you think I want you to calculate 2 times 2 times 2 is 8? Isn't 8 better than 2 to the 3rd? So use a little common sense. If it ends up being a nice number, kind of small, calculate it. If not, leave it alone. Are we good? All right, now I do want you guys to look at page 336. Once you get an idea of kind of what we're going to be doing here. Yes, sir?
I never got rule 7 down.
Rule 7. Okay, so I want you to get an idea. It's just the division one. It's the same as rule 6. It's just division. I want you to get an idea what the homework is going to look like. So I want you to look at classroom exercises real quick, just 1 through 6. Anything on 1 through 6, if I gave you that as homework right now, I'd be like, oh, what on earth? I bet everybody's looking at one question. Which one looks the hardest? Huh? 4? All right, let's do 4 and 5. 4, I agree. It kind of does look hard because you got some decimal exponents in there, right? Like, yuck. Nobody likes decimal exponents. Now, you've got 3, and doesn't that mean 3 times x to the 0.7th power? And then it's all times, so I really don't even need parentheses, times 81 to the negative 0.5 power times x to the 0.3. Looks a little yucky, doesn't it? All right, well, I got a couple x's here. What do I do with my exponents? Add them. That's my rule number 1. What's 0.7 plus 0.3? Isn't it 1? Shocker how they picked that. Makes it nice. All right, so I got this 3 over here. I'm going to leave that alone for now. What could I do with that thing? Well, first off, what do I do with negative exponents? Put on the bottom. So it's going to be like 1 over 81 to the 0.5 power. But nobody likes decimals. What's another way to write 0.5? 1/2. And what do we do with fractional exponents? We make them, starts with an R. Makes them radicals, right? 81 to the 1/2 power, isn't that just the same thing as the square root of 81? It's exactly the same thing. So what's the square root of 81? So that's the same thing as 1/9. So I times that 1/9 by 3. What's 3 times 1/9? What's 3 over 9 reduced to? 1/3. Final answer is, you got an x on top, you got a 3 on the bottom. Didn't that look a lot harder than what we actually did? Like the hardest thing we did was we took the square root of 81. There wasn't really much to do there. And I'll tell you right now, question number 5, and if you look at the next page, 337, question number 10. Question number 10, I call those easy vomit questions. Because just by looking at number 10, doesn't that like bring a little vomit to the back of the throat? Like, oh my God, look at that thing. It looks nasty. You've got fractions going on. You've got exponents going on. So we got 25. We got a variable x raised to the 2 root 2. You got a y to the 7 root 7. 15 x to the 5 root 2, y to the 2 root 7. Oh my gosh, that looks nasty. What do you think 90% of people taking an SAT when this is on the SAT will do when they get to that question? Skip it. They'll look at it and go, yeah, right, skip. And then the panic starts setting in because this is question 3, okay? And then they get to the next question, they go, oh, I don't know how to do that one either. And then the panic starts setting in. I don't know how to do any of this. I'm in trouble. I'm screwed. I'm an idiot. I don't know what I'm doing. My life is over, and I'm going to, right? That's exactly what they're trying to do to you. What do you think you do with the 25 and the 15? Reduce it. If nothing else was there and it was just 25 over 15, what would it reduce to? 5/3? Yes? Easy? What's my rule say I got to do with my exponents when I have the same base? Subtract. Now, -3 root 2. Doing that is nothing different. It is literally the exact same thing as doing 2x minus 5x. You got 2 of these minus 5 of those. You're combining like terms here. That's all you're doing. Nothing fancy. Yes? So because it's negative, where do you put those? In the bottom. The bigger numbers in the bottom. You put the leftovers in the bottom. So the x to the 3 root 2 goes in the bottom. How about the y's? Subtract. What's 7 root 7 minus 2 root 7? 5 root 7. So where do the leftovers go? Top. So that nasty problem, it really boiled down to reducing that fraction, 5 minus 2 and 7 minus 2. That's it. There's nothing else to do. Looks like vomit. Very simple to do though. Okay? As long as you know your properties and you know when to add, when to subtract, when to multiply, that kind of thing, you are good to go. If I gave you right now practice exercises 1 through 12, is there anything in those 12 questions that would cause you great demise? What's that? Say that again? It starts on 336. It's just the last, like right at the bottom, practice exercises. Yeah. So practice exercises like 1 through 4 is on the bottom of the page, and then it continues. So just 1 through 12. Is there anything that you're looking at going, what? There's a couple yucky ones, but I'll pretty much guarantee you they're easy. Yes? Like number 4? Is that the one you're talking about?
Yeah.
What would you do with powers raised to powers? What's our rule, powers raised to powers? Mm-hmm. You multiply, don't you? So what's a negative times a negative? Just a positive. They go away. So they take care of themselves in that case. If you wanted to, a negative exponent means you flip it. But then you got another negative, so you flip it back, and then you end up where you started. So, but they take care of themselves. So you just follow your rules. As long as the nice thing about these exponent rules is you can use any of the exponent rules you want in any order, as long as you don't break a rule. As long as you don't multiply when you're supposed to add or something like that, you can't make a mistake as long as you follow the rules. You have a powers raised to powers, you got to multiply. If you're multiplying, same base, you got to add. As long as you don't break the rules, you can't go wrong. Are we good? Now, if you do not have a calculator, I want you to come get one. Okay? Does everybody have a calculator right now? No? Will you go back to my desk? In that bottom drawer on the other desk. All right, everybody look over there. That drawer that he's pointing in, there's a whole bunch of TI-84 pluses. Those calculators are always going to be in there for you to use. I have 2 rules about calculators. Number 1, if you have your own, I want you using your own. If you don't have one, grab one while you're there. If you don't, in fact, anyone, if you do not have a calculator right now in front of you, please go get one. My rules about calculators are 2 things. Number 1, if you have your own calculator, I want you using your own. Why would I want you using your own calculator? Because that's the one I want you getting used to, because that's the one you're probably going to use on the SAT. I'm not even saying you can't use mine on the SAT, because they're going to be there. I'll let you check them out. Use them on the SAT. I want you getting used to the one you're going to use on the test. And yes, different calculators, you have to type things in differently. So I don't want you getting mine and you're used to a different one and you had to use parentheses, and where the other one you didn't have to use parentheses, and it's just a headache, right? So that's rule number 1. Rule number 2 is you're only allowed to use a calculator in here that you can use on an SAT. So like the answer to the question is, can I use my phone as a calculator? Well, can you use your phone on the SAT? No? So find one. There's a drawer full of them over there, so go use one of those. Okay? Those are my only 2 rules about calculators. Now, the next set of problems, that's exactly what they are. All you have to do is be able to calculate what those are. Like if you look at number 6, it says 6 to 3. I need you being able to type that in correctly. Now, how you type that in will vary. It depends on the type of calculator you have in front of you. If you have one of this type, these TI-84s, these TI-84s have the operating system called MathPrint, which means you make it look exactly like that. That's the goal. So what would be the first button I would hit? 6, then what? I gotta have my exponent. I gotta move the cursor up into the exponent part, which is the up arrow above division. So I'd hit that exponent button. Then I want square root. So my square root button is the second version of the squared button. And then I'd hit 7. What's the next button I want to hit? It's not plus.
Right arrow.
I want to end that square root. If I hit plus, that square root symbol is going to continue. I don't want it to continue. Maybe I do want it to continue for certain problems, but if I want to end it, I have to end it by pressing over, and then it stops that square root symbol. Okay, and then I hit plus, square root again, 3. The correct answer to this problem is 2,550.305. If you can't get that on your calculator, we need to talk right now. Now, looking around the room at different calculators you guys have, does yours have MathPrint on it? Does it look like mine? Oh, you have one of mine.
I have one. It looks just like Cadence, and it has like a little button I think you can
Mine
press
has
on it.
Yeah,
Like this type. So is that like the same thing that we use on the
kinda, yeah. But some calculators you do have to be very, very careful on.
Please excuse me for a quick announcement about schedule changes. Teachers, you were just sent an email with an update, but students, at this time, we have gone through all the 9th through 12th grade requests. So if you have not been called down, please sign up
Yeah,
again.
perfect.
No more schedule changes after Tuesday. So if you need something done, you need to be signed up to talk to a counselor by Tuesday lunches in order to get your schedule changed. Thanks and have a great weekend.
All right, this is one of the ones I was looking for. Because this, even though it's a Texas Instrument, come on, focus. Can you guys see that? Whoa, that is really fuzzy. All right, is that okay? Can you guys see that? Can you see the blinker cursor? Yes? All right, so, in fact, I want to do this. Ready, set. Stay. Don't move. Don't move. Dang it. All right, well, I'll just pause it because